Sure to first recap the generalized eigenvalue problem because it's really important. So we have AV. Now instead of lambda V, which is your eigenvalue times the vector, we have lambda BV. So we want now we want the determinant of A minus lambda B equal to 0. And then you write A like, you do everything. Now you can do it more generally. So your eigenvectors could be like this, V1, Vn, and D, your diagonal matrix, has these entries if I is j, otherwise it is 0. And the idea of pencil is that the set of matrices of the form A minus lambda B, where lambda is the complex number, it is called a pencil. So the term pencil can also refer to the pair. We say pair A and B. So it's a matrix pencil. But if B is invertible, then the original problem can be written in the form B inverse AV is equal to lambda V. However, in most situations, it is preferable not to perform inversion, but rather to solve the generalized eigenvalue problem as stated originally. So if A0, A1, AL are n by n complex matrices of some non-negative integral L, and AL is not 0, then the matrix pencil of degree L is just matrix valued function L of lambda is equal to I from 0 to L, lambda I AI. But particular case is that the pencil A minus lambda B, you only need to know that this is A or B. And also you should know that this is the set of eigenvalues of A and B. So in other words, this is the spectrum of the pencil. So we solve generalized eigenvalue problem. Traditionally, we use QZ algorithm, which is a generalization of shared decomposition and those ideas, and they call it QZ decomposition. I mean, this is like something like A is Q S Z transpose, B is Q T Z transpose, and Q and Z, these are unitary. I assume you are a physicist. S and T are upper triangular. I assume you are a physicist to appreciate these things. So let's talk about sparse generalized eigenvalue, but I want to use smooth optimization for that. So if you have generalized eigenvalue problem for pair A and B, the problem of finding a pair lambda and x such that AX becomes lambda BX, but don't forget that A and B are just n by n matrices and your eigenvalue is real. So the problem is that lambda max of A and B is the solution to maximization problem of X transpose AX X transpose BX. But what if, in other words, you can say this is maximize X transpose AX over X subject to X transpose BX is equal to 1. So in generalized eigenvalue problem, eigenvector is not expected to have many zero entries, which makes the result difficult to interpret, especially when dealing with high-dimensional data. So I use majorization, minimization, or minorization, maximization. I'm talking about how to deal with non-convexity of the sparse generalized eigenvalue problem because I want to add some L0 norm, and that makes it non-convex. That's why you need to use methods such as majorization, minimization. This is MM method. Methods like this, methods like difference of convex functions, methods like successive convex approximation. There are many methods to deal with non-convexity or non-concavity of your problem, depending on minimization or maximization problem. So the interesting idea is that you have a very complicated function. You want to maximize it, and so you do it by some approximation. So you're minorized by a quadratic function, and then so at each time you try to find a minorization, which is tangent here and has the same formula, and for that you solve the maximization problem. Becomes this, and in the next step again you find a minorization, and you find the maximized, and again you try to find an approximation which is tangent and equal to that, but it is majorized by the original function, and successively you come up with the final solution, or very luckily you arrive at here, depending on, for example, how you're approximating it. And so this is the how I apply quadratic minorization. And so your original sparse generalized eigenvalue problem becomes a sequence of regular generalized eigenvalue problem. So given a matrix, but symmetric matrix A in Sn, and a symmetric positive definite matrix, we call it Sn++. It is both symmetric and positive definite. The main problem of interest is the following L0 norm regularized generalized eigenvalue problem. So we want to maximize X transpose AX minus rho. Don't forget this is the zero norm, L0 norm, subject to X transpose BX is equal to 1. You have seen this many times in sparse PCA, in sparse CCA. So this problem is really non-concave, discontinuous over non-convex set. So what can I do? I approximate this guy. I say L0 norm is equal to I from 1 to n. This is the sign of absolute of all of the entries coordinates. And so I want to replace it again. Replace it by some nicer surrogate functions. GP. Your GP could be anything. XP, it could be, your GP could be log of 1 plus XP over log of 1 plus 1P, but P is greater than 0. Here P is between 1 and 0. And also your GP could be 1 minus e to the power of minus absolute of x over p, but p is positive. Geometrically, for example, the first one could be this. This is the first one, so it's x to the power of p, but p is between 1 and 0. The second one could be like this. First, it's nice, but it's like this. First nice, but it's like this. And the last one, you can write it like this. Okay, so pick just one of them, one of the surrogate, it's enough. I typically like this one for many reasons. So in my article, I use this. And so let's just maximize x transpose ax minus rho I n gp xi subject to x transpose bx is equal to 1. This is continuous, but still non-concave. That's why you use MM method to deal with this non-concavity. So suppose we want to minimize f of x over x in Rn. MM approach optimizes a sequence of approximate objective function that majorizes f of x. So starting from physical point x naught, and then successively we solve a set of minimization problems. U of x, but at point xk, the approximation and the original function are the same. So this is the majorization function. If you want to do a minimization problem. So you have a very complex shape. So this is f of x. And you approximate it by u. So this u is this blue line. You approximate it by u. So you hope to get to here and not to fall in those local minima. But since our problem is maximization, we want to do opposite. So we want to find minorization maximization. So it's something else. But, the definition, I just want to say that for minimization problem is this, and the global upper bound for f should coincide with f at xk. In other words, f xk plus 1 is less than u of xk plus 1, but at point xk they are the same, so this one is u of xk, and this is your f of xk. So you go down. But for maximization, which is our problem, we need to minorize it by a surrogate function. So your quadratic minorization, I mean, what you are doing is the opposite. So you have minorized by this quadratic. So, and this is the equation for this quadratic. But the original function is surrogate I from 1 to n, and don't forget n is the number of pixels if you are doing image processing, the number of features if you are doing anything. So in general, n is the number of features. But you know that at these points, first the value of them should be the same, and second, their tangent should be the same. The same slope. At these points, you have the same slope. So putting these two constraints, we have for first constraint that you just need the value of them to be equal to the value of approximate function, which is a quadratic function, xak squared plus cak. And as I said, the slope of the original function should be equal to the slope of the approximated, which is a quadratic approximation of the original function. So if you solve this, you get your coefficients and everything is solved. So objective function x transpose ax minus rho I from 1 to n gp of xi is minorized by the quadratic function x transpose ax minus rho w I k at k's iteration xi2 plus cik. And so your problem is you want to maximize x transpose a. So this goes inside, this is the second order and this is this coefficient of second, so this one can go. So finally I can write this as rho diagonal at point wk x minus rho I cik. Don't forget that this is constant. This is the offset of that. So because it's constant, it is fixed, so we don't care about it in the optimization, in the maximization problem. So so I want to do it for the surrogate function. The surrogate function that I want to use is absolute of xi to p, where p is between 1 and 0. So let's do it. GPXIK is equal